Howdy folks, so today I want to give you an overview of the average rate of change, which is something maybe you've looked at before. We're going to change our perspective slightly in this class. So the average rate of change for a function is given by this expression right here. It would be f of b minus f of a all divided by b minus a. So what we're saying here is the average rate of change, and sometimes we'll add on the interval from a to b, is a way of talking about, on average, how do the y values change over the course of this interval. So let's go ahead and apply that to this function right here. We're given, in this case, the function f of x is equal to x squared. And here we're being asked to compute the average rate of change for that function between x equals 2 and x equals 3. So let's go ahead and compute this, and then we'll look at what we've done. So the average rate of change on the interval from 2 to 3 is given by f of 3, the second value, minus f of 2, that's the change in the y values here, all divided by the change in the x values. So if I go through to compute f of 3 would be 3 squared, and we're going to subtract from that f of 2, which would be 2 squared, all divided by this 1 in the denominator here. And if we finish this out, we would have 9 minus 4 over 1, which comes out to be 5. Okay, so great. The average rate of change between x equals 2 and x equals 3 for this function f of x that we're given right here comes out to be 5. What on earth does that mean? Well, if we were to go actually plot these ordered pairs, so here was the ordered pair 2, 4 on the graph of this function, 2, 4, and we got that, that's our f of 2 value right there. And if we were going to plot the ordered pair 3, 9, which we obtained, there's the ordered pair 3, 9 on the graph of this function. So what is it that we've done? Well, what we've done is we've computed the average rate of change, which would be the slope of this line. So even though this graph, this function here, let me see if I can get this graph on. It may not play nicely. Let's give it a shot here. That's pretty close. So the graph, oh, no, that didn't quite do what I wanted to. Oh well. The slope of this line right here, and it's supposed to be, I apologize folks, it's supposed to be passing between these 2 points here, but the slope of this line is equal to 5. And it is the slope of this line which is our average rate of change. So it's if we were to take our graph, which is not necessarily the graph of a line, that's an important thing to notice, if we were to find the slope of the line connecting those 2 points, that slope of the line gives us the average rate of change. So what I'd like you to do now, or we'll work together, is let's go ahead and find the average rate of change on a different interval. So let's find the average rate of change for f on the interval from -2 to 1. Okay. Well, this would be f of the right endpoint, f of 1 minus f of -2, all divided by 2 minus 1. Excuse me, that's incorrect, folks. All divided by 1 minus -2. And so if I were to compute f of 1, that would be 1 squared. And we're going to subtract from that -2 squared, divided by, notice the denominator would be 3. And so what we end up with is 1 squared is 1, minus 4 divided by 3. That would be -3 divided by 3, which is equal to -1. The average rate of change over this particular interval is -1. I think it's good to, again, graphically look at what we've just done here. So here is when x was equal to 1, we were at the ordered pair 1, 1. And when x was equal to -2, we were at +4. And so what is it that we've just done? I'm just going to go ahead and hand draw this. Won't be as nice, but there's the line that connects those 2 points on the graph of this function. That's the connecting between the x value -2 and the x value 1. That's what we're seeing. There's the x value -2. There's the x value 1. We've connected between them. And the slope of this line right here that I've just drawn, the slope of this line is -1. So the insight that I want you to make in this case is that for this particular function f, this graph f here, which is the function f of x is equal to x squared, for this particular function f, the average rate of change is not constant. Well, a linear function is a special type of function. A linear function is a function that can be written in the form ax plus b, where a and b are contained in R. Unless otherwise stated, unless I give you a different domain, the domain of a linear function, that is this function right here, is the interval from minus infinity to infinity. And provided that a does not equal 0, as long as in fact you know this already, as long as the slope of the line isn't 0, and we don't have a horizontal line, then the range would be from minus infinity to infinity, such as this linear function that I've shown you right here. So here in G, here for question number 7, I've given you the linear function g of x. And we could see that the domain here is all real numbers, and the range here is all real numbers for this particular linear function. And that happens whenever the a value is not 0. So for fun, what I want you to do is, or what we're going to do is we're going to compute the average rate of change for this function between x equals 1 and x equals 2. So let's go ahead and do so. So if I were to compute g of, so let's go ahead and just state what that is. The average rate of change on the interval from 1 to 2, that average rate of change would be not f anymore. We're not using the function f any longer. What function are we using? We're using the function g. So that would be g of 2 minus g of 1 all over 2 minus 1. And if I compute g of 2, that would be 3 times 2 plus 2. That's my g of 2. And we're going to subtract from that g of 1. I'm going to move off the line here just a little bit. Sorry about that, folks. And if we were to compute g of 1, that would be 3 times 1 plus 2, all divided by 2 minus 1, which is 1. And that gives me here, I'm just going to add it up, 6 plus 2 is 8. And we're going to subtract from that 3 plus 2 is 5, divided by 1. And that comes out to be the fraction 3 over 1, or the number 3, for that answer there. Okay, I think you've got this process of computing the average rate of change for any old function. What I'd like you to do is, on your own, I want you to compute this average rate of change. So please pause the video and mimic exactly, for this problem right here, you're going to mimic exactly what we did up here, except instead of using between x equals 1 and x equals 2, you're going to do between x equals negative 3 and x equals negative 1. So pause the video and give that a shot. Okay, so folks, what you should have found was that the average rate of change, and make sure you have the work to back this up, the average rate of change between x equals negative 3 and x equals negative 1, you should have found, after you do all the work, you need this, that average rate of change should have also been 3. And there is not a coincidence there. Okay? So again, going back to the image of this, here we've got the graph of g of x. And if we initially found the average rate of change between x equals 1 and x equals 2, and we found the slope of the line connecting those 2 points was equal to 3. And then what I'm hoping that you just did was we took the average rate of change between, here's where x is negative 3, so that's this point on the line. Here's where x is negative 1, that's this point on the line. And you just computed the slope of this line connecting the 2 points, and you should have found that that's also 3. What you should see is, no matter which pair of points I pick, I'm going to get an average rate of change of 3. And in fact, we notice that for, now this is not always true, we notice that for specifically linear functions, remember what were the linear functions? The linear functions were the ones that could be written in this form, ax plus b, that when you go to find the average rate of change for linear functions, that it's constant. It doesn't vary. Okay? In later courses, you'll see not only is the average rate of change for any linear constant, but it's also what's called the instantaneous rate of change. Okay? This property is unique to linear functions. They are precisely the functions. So in fact, it is the fact that linear functions have a constant rate of change that's actually what makes them linear, now that we've learned this. Okay. Of course, you shouldn't be surprised here, but linear functions obtain their names because the graphs of linear functions are lines. Okay? And you saw that with this linear function g of x right here, 3x plus 2. Of course, the graph of a linear function is a line. But what I want you to start to think about is that we can talk about average rates of change, but for linear functions, the average rates of change are constant. Again, you want to contrast this example that I'm showing you, right here. I want you to contrast that with the original example that I gave you when we looked at this, where in this case, here for one pair of points, the average rate of change was 5. For another pair of points, the average rate of change was -1. And so the average rate of change was not constant for the function x squared, but it is for these lines. Okay.